So let's continue where we were. If there aren't any questions, we discussed 3-4 different instability mechanisms for critical heat flux, 4 of them for flow boiling. One of them is the experimental one. Typical, like in this particular experiment, somebody was asking, you were asking about, in this particular experiment, the high heat flux is arranged in a channel which is 3-sided heating, and electric heating is coming from the bottom. You can put, to create large amount of heat, like 400 watt per centimeter. This is one of the cheaper ways to do it. It's very hard to have a thin film and have it at that high level. So you have a high heat flux here, then you converge and you convert, all heat is going up, and so like a flow, you can go from 100 to 500 watt per centimeter square. So then you can electrically control the amount of heat that you're going into the section, and look at from the top, a glass, sapphire glass or something. You have to make sure that these are leak proof. These are cartridge heaters inserted into the electric heaters, this wedge shaped electric heaters. And you need to have a flow loop and a module to look at. In this case, he's looking at it from and one of the instability mechanisms that we mentioned, he sees that, let's see, where can I, yeah, right here. As certain heat fluxes increase and you try to feed in liquid into a high heat flux thing, you see certain channels, it splashes back. It simply doesn't want the liquid to enter. So this was one of the mechanisms, one, that I mentioned. These were microchannel solid walls, and he's having some variations between 1 to multiple because you have different inlet conditions to these different channels. But roughly for one channel, you can reach that kind of a inlet instability itself. So this was one of the 4 different mechanisms. Because of these different mechanisms, there are many critical heat flux estimators, and one of the more popular ones, looks rather messy, I will try to show you here, is if you were trying to call Q double prime PM as a critical heat flux formula, it's given in terms of PM naught and a constant K. There is this. This is Kato and a Japanese group, reasonably. Let me see if I can make it a little better. So PM naught and a constant K, if there is subcooling, there is a correction. If there is no subcooling, that is 0. And you define a bunch of other heat fluxes, PM naught 1, naught 2, naught 3, naught 4, naught 5, a bunch of non-dimensional surface tension numbers, C, L over D, the length of the hydraulic diameter of the channel, and depending on the length and hydraulic diameter, you have different values of the constants. C that appears actually in PM naught 1. Then you go through, is your vapor to liquid density ratio is less than 0.51? Is this number less than that number? If that is it, then this Q double prime PMO is equal to PMO1. Then if it is the other way around, and so certain logical constraints, you can set it up. And the reason it looks a little weird like this is because it's probably trying to cover 2-3 different mechanisms of CHF, and not all of them. And so it is for you to get familiar with, say, 1 or 2 of them. If you had to design and you were curious, is your heat flux too much? What you will do is you can go through 1 or 2 of these that are relevant to you, and then have a feel for order of magnitude of. So there is a Bowring one he has compared. Then for saturated one, I just showed you Kato and Ono. So there are a bunch of different estimates there, and then after everyone reviews other people's correlation, they propose one of their own, so the number of correlations keep increasing. Okay, the question is, obviously it's not a bad idea to propose your own one if it covers a larger amount of a data set. But basically this is the Kato and Ono CHF. So this particular he has a bunch of other references for rectangular channels, and I would let you, I'm not going to go into a very detailed quantitative estimate. As I told you, these are estimates that you need to keep in mind when you're designing, and be open about it, that they are not. You'll have to read up more on a specific flow boiling critical heat flux as opposed to the critical heat flux for pool boiling, which has also a bunch of different correlations that which Professor Ghosh Dastidar reviewed, and you wanted to look at them, you could find them in the reference section of on the pool boiling TOMI reference that I have. Okay, with that I will proceed to somewhat newer stuff and go to look at a few problems to discuss how we compute. So let me look at a boiling flow heat transfer coefficient problem, and as I read it I will write some things here. You have a rectangular cross section horizontal flow boiler. The height is 5 millimeter. Width is 10 millimeter. It's one of our kind of flow boilers where you have a splitter plate and you have liquid and you have a vapor. Both m dot liquid at the inlet is 0.0075 kilogram per second. M dot vapor is 0.0075 kilogram per second. The inlet pressure is 120.1 kilopascal. Relevant fluid pressure given pressure, this is R123, fluid is R123, so you can look up this refrigerant properties. It is actually given after having looked up, it's given as a part of the problem. You're heating from below, so you are doing uniform heating, so Q double prime wall X is equal to Q double prime wall bar is equal to 50 watt per centimeter square. So first question is, what should we have exit quality? So inlet quality is equal, m dot total is m dot v plus m dot l, and you have equal to at any x, so we put at x equal to inlet, is 0.0075 times 2 kilogram per second. So X inlet is equal to m dot vapor at inlet by m dot total. So it's equal to half, is equal to 0.5. So the first question is L equal to what for X out is equal to 0.75. And it is uniform heat flux method of heating, so that's relatively simple. How would the quality vary for uniform heat flux method of heating? Do you remember that? And what was energy balance for quality looking like for uniform heat flux method of heating? See, it's asking first question is Xx equal to, this was I could call it 0. The second is Xx equal to what? Then the second question is Hx versus X is what? How does heat transfer coefficient vary? And what is the decomposition as per Kim and Mudawar of this Hx between convective boiling and nucleate boiling? This we don't know whether it's going to be annular because this ratio if 0.5, if X in, so what is X critical for annular to non-annular? We don't know. Equal to what? So what I'm trying to say is that if X critical from annular to non-annular was say 0.6, then X in is less than X critical annular to non-annular, and as you remember, in that case you first have a plug slug flow, and after X critical you then get to be annular stratified type of flow. So there would be a region here that would be non-annular, and you don't know how long that would be. So you can't really tell whether it is fully annular or partially non-annular and annular. That's a problem I would try to define next time to decide. Suppose, but on the other hand, if X critical annular to non-annular was 0.4, then it would look like right from here an annular flow. So that's a different question. Okay. Right now we are not talking about flow regimes and pressure drops, but there's a valid question to try to visualize and ask. Okay. So the third question was, if we knew that, what is T wall of X? If we already knew the heat flux, then there is nothing to find out about heat flux, where we Hx and delta T we may have to find out. So the very first question here, if you remember, is that for prescribed energy balance or for that particular case was dx caret was equal to the boiling number times psi q of x, which is equal to 1. There is no spatial variation in heat flux. You can see that, is that right? If you don't see that from the formula, it's a very simple derivation. What it says here is the energy balance I had written down last time. When I did energy balance here, what did I write down? It was equal to Q double prime wall X equal to Q double prime wall bar was equal to dm dot v dx HFG. You remember that when I did in the morning this derivation? So now that since this is known, I'm not going to plug it in terms of Hx, okay? And then I'm going to say that this implies Q double prime wall bar equal to m dot total times dx times HFG, and that tells you that dx is equal to dx was equal to Q double prime wall bar by m dot t was g times pi by 4 d square, d hydraulic square, and HFG, and I can write this as x caret and then put d hydraulic here. So it actually becomes equal to, I think I missed something here, there was a pi d, this was pi d hydraulic here, pi d hydraulic here, I missed that. So there was a pi d, 1 over pi d hydraulic over here, and there is 1 over, I'm trying to show this result for uniform heat flux method of heating. There is, I think I can erase this for the time being. And you have Q double prime wall bar equal to G times pi by 4 dH squared is m dot total, HFG into 1 over pi dH into dx, and for x is equal to x caret dH. So I'll write it dx caret, x is equal to dH times x caret, where this is a non-dimensional distance. Then pi dH square it becomes, and pi dH square cancels with that. I should have gotten a factor of 4, and I'm missing that here somehow. Did I include that in my VL definition? I doubt it. I am getting a factor of 4, is that right? So anyway, what we get here is G HFG by 4 dx d caret and I'm getting here an equation called dx caret equal to Q double prime wall bar by GHFG times 4, and I'm going to call this boiling number. I didn't have this 4 in my notes, okay? Do you see any bugs here in the definition, or you don't see it? It's surprising. That's going to change some of my numbers because that factor 4 should have been there in the part of the definition if I'm going to use it, okay? So with that, now we have to solve this problem. So what are we getting? This is a constant. So this means x is a constant xx equal to x in plus BL times x caret minus 0, and that is the value of how how this varies linearly. So in other words, for me to not have to do certain things, I will probably have to change some numbers as I go along. So we get the first part of it. We know how quality varies linearly, and it looks like this graph here. So if I for a moment, if I made it from 50 to 50 by 4, then it would be 12.5 watt per centimeter squared as opposed to 50 watt per centimeter square, and then I would get the answers that is given here. The quality varies from 0.5 to 0.75, and the distance L is given by this formula here, x out minus x in. Oh, okay, now I see what we have done here. This is this is correct for, no, let me fix that. I think the definition used in the formula sheet is a little different. It's based on height, okay. So I think BL is H, okay, so I should have done that first. Let me see how that, how is the boiling number defined is, okay, I think what I have done here wrong is this. I was doing in terms of hydraulic diameter, but this is a channel problem, so I could have simply done, I would have redefined it for this channel problem somewhat differently. Otherwise, I'll have to redefine dH in terms of 4H. The amount of heat that's coming in is simply Q double prime width times is heat that comes in. There is a factor 4 that I'm trying to correct here. If you use the height H, you probably won't get, hydraulic diameter dH is equal to 4 times H, and somehow I think that needs to be used. Let me, anyone here is quick enough to notice where the factor 4 is coming from? Yeah, I was doing a tubular geometry right here. I think there is a mistake on that side. Okay, I think that the issue here is the definition of x caret. X caret is not defined as dH. I have defined x as h times x caret, and that means dH is equal to 4h. Okay, so there is no there. That's why there is no 4 in there. Okay, so you fix that. You fix that particular definition that way. I'm surprised though. I'm surprised at that. No, I have defined x caret as x by dH. So there may be just an error, okay? I will not worry about it. I'll fix that and get back to you. So here I have Q double, so we compute the boiling number, we compute the Prandtl number, we compute the liquid only Reynolds number, which is defined as GdH by mu liquid, Weber number, and the reduced pressure. With that, we have all the information that we need to have to use the Nusselt number for flow boiling for given heat flux. So all these were the properties for R1, 2, 3. You go ahead and look up the critical pressure, saturation temperature, density, vapor, viscosity, this and this. The mass flux, do you want me to go through the, I think let me go through the whole thing here rather than. So the questions are set up. if you, depending on whether you, how you define your x caret, you may have a factor 4 or you may not have, okay? That's how it depends on that. So the hydraulic diameter is 4 times the cross-sectional area by the perimeter that is heated. This is a rectangular cross-section, so H times W by W, only the W is the heated perimeter, so it is 4 times H. The inlet mass flow rate m dot V in and m dot L in has already been noted in the picture, so I won't write it. X in, X out, and heat flux is given, and so what we are saying is X out minus X in by L should be equal to the boiling number, because this is equal to dx. Actually, this is being done dx dx as such, so it should have been fixed. Okay, yeah, that is why there is no. While writing this, I would say that it has been written here. X double caret is defined like this, and X double caret is being used. That's why there is no 4, not X caret. Okay. Do you follow what I'm saying? See, this equation was giving you dx caret equal to 4 times boiling number. But if you were to replace X double caret, and this is X caret, X equal to 4H X caret, and if I call X equal to HX double caret, then X double caret is equal to 4 times X caret. So the solution that he is plotting is based on this dx double caret. So his answer isn't wrong, BL. So we have this is at L over H rather than L over 4H equal to BL. Otherwise, it would be L over 4H, okay? X double caret. So based on this, we have this number, X out is 0.75, X in is 0.5, L is what we want to find out, and H is given is 5 into 10 minus 3 meters, and the value of boiling number has been computed, which is defined correctly. It's 0.0099 is equal to GHFG Q double prime wall bar by GHFG, so it becomes 0.0099. So it says that the length of the boiler should be equal to 0.1264 meter or 12.6 centimeters. So if you have 12.6 centimeter long, this dimension, you are coming at this much liquid and this much vapor. This is uniform heating. Then quality is varying, and there is, in this particular question, there is no question about what is the flow regime. Is that right? It is just simple energy balance. Yeah, and you get the length of the boiler, and you answer the first question, how is the quality varying? Now the next question is, what is the heat transfer coefficient, Hx versus x? So now you know x versus x. The linear variation, correct length, so this graph is correct, okay, because it is in raw variables, so this graph is correct, okay. At 0.12 meter, you have straight line. Now let's ask what is to get Hx we need to get Nusselt number for the flow boiling. Hx equal to as a function of x is equal to what? That was the first question. So or rather the second question. So that is like asking Hx dH by K liquid is called Nusselt sub x, and you ask what correlation to use. What correlation to use? This is a saturated boiling and inside the duct. So there is only one correlation that I looked at, and there were a few others that there was another one that Professor Ghosh Dastidar has mentioned. Which one did he put? Do you remember from yesterday's lecture? Which correlation he used? For flow condensation he used someone else's. For flow boiling, I think I wasn't there in that particular lecture, so he must have introduced another correlation. But anyway, let's go to Kim and Mudawar, which is a 2014 correlation, the latest one, and see what we recommend there. So you go to either the Kim and Mudawar one, or you go to my lecture notes, and in the lecture notes for flow boiling, my lecture notes recalls what Kim and Mudawar has in his paper, which we reviewed in the morning. And what do you get? Kim and Mudawar correlation looks like this. Yeah. So what he calls a universal correlation for pre-dry out situation, flow boiling. He goes ahead and computes Hx nucleate boiling through this formula, and then he computes convective boiling and takes square and square root. The only thing that is experimentally measured is this. These are just some intermediate formulas, so you don't need to trust the decomposition, but you should be able to trust the total value of the heat transfer coefficient. Notice that there is he is using a Martinelli parameter Tt in this, and I have put a tilde on this. So let's look at all these definitions in my notes, and then we proceed from there. It's a lot easier to implement this on MATLAB, where you write down the formulas and it will do this. And the tutorial MATLAB is available. If you click on it, you can look at the definitions and the code and change it. So what is RE liquid and what is Prandtl liquid? So we use Kim and Mudawar. The parameters we need are RE liquid, Prandtl liquid. So RE liquid is G1 minus X dH by mu liquid. At any given X, that is at any quality, that is the value of this. The parameter that you need here is reduced pressure PR and Prandtl number. There is also, all these numbers are defined: boiling number, Prandtl number, REL, RE liquid only, and Prandtl liquid. All these formulas are defined. This surface tension parameter Weber number is defined, and this X tilde Tt is defined. The perimeter heated was W, and PF. Let me see what was PF. Also W. Wetted parameter wetted parameter and the heated parameters were the same. Sometimes you can have liquid flowing on, say, bottom wall, and you may be heating 3 walls. So then the wetted and heated parameters may be different. So in this case, pH equal to Pf equal to W, which was equal to 10 millimeter. So I'm trying to say that looking at the formula, there is nothing here that you don't know, because dH is equal to 4H, you know that. dH equal to 4H, every parameter is known. Okay? I'll just, rather than writing things, I'll just show you what we get here. The value of liquid Reynolds number is 7831 for at inlet at 0.5, and at inlet we compute the Lockhart-Martinelli parameter, we compute this HL, we compute the value of HX nucleate boiling, and at inlet I also compute just for a specific number at inlet HX convective boiling, and we get 8126 watt per meter square Kelvin, the value of the heat transfer coefficient. Now what you're going to do is to do that for X inlet, for every X up until 0.75, you just put different values of X, okay? Quality, because it's a linear variation. So you automate this up and you plot this, and you get this H full total, and this is the nucleate boiling and this is the convective boiling, okay? And I told you that I don't trust the breakup, but we do get the breakup also if you use this correlation. So the question now arises, what do we mean by convective boiling? Now that you have these numbers, now can you take a guess and tell me what does he mean by this much is coming from convective boiling and this much is coming from nucleate boiling? Is there any clear or intuitive definition you would have? What would convective boiling heat transfer coefficient mean? Let me ask you this question here. It's an important question because it's something that is avoided, and you get in literature and you start plugging in numbers and you don't understand. So anyways, the first and second part what was there, but I'm asking you a conceptual question. So you have, suppose it was all annular and your X in is greater than X critical from plug slug to annular, and I have two situations. Suppose I have, this is my delta X that actually happens, physical reality. Physical reality is an annular flow over 0 to L, and part of it is lot of nucleate boiling is going on, and then slowly my nucleate boiling might get suppressed if it is too thin a film, okay? Now Hx, obviously Hx at every location has a component of nucleate boiling and convective boiling. What do we mean by convective boiling? That's my question. Nucleate boiling, everyone understands, are bubbles coming and getting out. Due to the temperature difference, whatever
between the wall and the...
like, yeah, I think if in a moment, if you ask this question, that if the morphology of the liquid vapor interface remained the same, okay, and there was no nucleation going on, suppose, then for that to be sustained with boiling, there is only convective boiling, means just at the evaporation at the interface, you would be able to, and the liquid flow rate, vapor flow rate is same, and liquid vapor interface is the same. Hypothetically, it's a mental imagination, with no nucleation, if you are able to achieve the same interface configuration, it will happen for a certain heat flux or a certain void temperature, which won't be the same as in the real case. But you hypothetically find that thermal boundary condition for which you have the same inlet, outlet and liquid vapor interface, and when you find this, the hypothetical situation, same delta x same, no nucleation, and you have Q double prime wall hypothetical, and the corresponding thermal equivalent here is T wall hypothetical, same inlet conditions. This is what we mean a purely convective case. Suppose I define a purely convective case is one like this. Then if I had a theory to run and I just suppress nucleation in my CFD code, and then if I find Q double prime wall X hypothetical no nucleation, same morphology is achieved for certain condition. You may, for annular it is easy to achieve same morphology. You may doubt that whether you can achieve the same morphology or not if the flow is slightly different regimes, but that is, and then you have this TWX hypothetical minus T sat P in. You can get a meaning of what HX convective boiling is. And so you have HX convective boiling and HX nucleate boiling, and you are superposing them. That's one way to define what you mean by decomposition between convective boiling and nucleate boiling. Okay? It's not a very clear definition. It's a lot of hypothetical things. So unless a person tells you what he means by convective boiling, but if you agree with this, then it's very simple what HX convective boiling is. Remember what Professor Ghosh showed you, that for any thin film, the temperature profile is linear, and this is a thin film annular boiling, suppose. Then HX convective boiling would simply be K1 times delta of X, and if you know the film thickness variation, then you know your convective boiling heat transfer coefficient. If you had film thickness sensors mounted, you could actually experimentally tell and define what you mean by convective boiling heat transfer coefficient. Anything else between H total measured and this HX convective boiling, you dump it into HX nucleate boiling. This is the way I would go about doing it. If we do this, we will find that Kim and Mudawar's decomposition is wrong. It doesn't work that way. Then all you do is you change the fraction, make it right, but the total remains right. So I'm just telling you an answer that I have checked. Okay. So that's a very important question rather than just plug and chug, because we get carried away with plug and chug. Okay. So coming back, we were able to answer for this flow boiling situation what is the total heat transfer and what is this nucleate boiling, convective boiling. So if I say that I don't trust, what do I have to do? I have to if I verify that my X inlet is in the annular regime, and if suppose I have a void fraction correlation, my void fraction would give me my film thickness in this particular annular regime. See, what is the void fraction? Suppose, remember what is void fraction? Epsilon was equal to AV at X by A total. And what is AV of X for this simple situation? This would be H minus delta of X times the width is my cross-sectional area of the vapor times H times the width is the total cross-sectional area. So I would have gotten my 1 minus delta X by H would have been this, and if I know my film thickness at inlet, suppose I can predict, if I know my epsilon, I can tell you my film thickness at the inlet. If I can tell you my film thickness of inlet, I can tell you Hx inlet, convective boiling, and if that is not this number but it is this number, I will multiply it by that number and say my Hx convective boiling is off by that much, by that factor. And then I will have to come back and change my nucleate boiling so that I get the same answer, and that way you can come closer to actual convective boiling and nucleate boiling rather than a mathematical decomposition. Do you understand what I am trying to say? If you give a meaning to convective boiling, meaning due to convection and not due to nucleation, and you give this meaning, then you can actually decompose it. Otherwise, it will always remain as some mathematical jugglery, because you are only correlating HT and you are finding a formula for it. That's an important observation, particularly if you wanted to build a boiler where you wanted to tell what the film thickness was, okay? Liquid film thickness was, which is not there in this correlation. It's just a total heat transfer. So with that, what the next question was, what's the wall temperature? So we have Hx versus x, quality, and quality versus distance. So I can replace quality by another line distance here. And magnitude of wall temperature minus saturation temperature. So my wall temperature is saturation temperature inlet by heat flux by Hx, and heat flux is uniform. My Hx versus distance is known, okay? The heat transfer coefficient was, so we can tell that my wall temperature is not uniform, my wall temperature is rising in order to keep the heat flux safe. Why? Because my film thickness is reducing, reducing, so my heat transfer coefficient was going up. So as the heat flux is the same, you need smaller temperature difference for smaller thermal resistance. Actually, the other way around, it should. The graph has been, the total heat transfer coefficient is dropping, not rising. Only the convective one rises. So let me correct myself, okay? The total is dropping because the nucleate boiling component, so dropping is more dominant than the convective boiling components rise. So the total was dropping, and that's why my wall temperature had to. So looking at this coefficient, it was not thin film suppressed nucleation boiling. If it was thin film suppressed nucleation boiling, what I said would have been right. K liquid by delta, my delta is falling, my heat transfer coefficient is rising. But what did we find? That was wrong. If I trust his result, and there's less reason to doubt this result because that's an experimental result, okay? So what was happening? Nucleate boiling was a pretty important contribution to the heat transfer. As nucleate boiling started reducing, the total heat transfer coefficient dropped pretty significantly, and the rise in the convective boiling did not offset it, okay? Even though it is an annular boiling. And I will show you in the third day and all that there, as the amount of nucleate boiling and convective boiling components highly depend on the mass fluxes. At lower mass fluxes and thin films, convective boiling is okay and suppressed nucleation comes. But at higher mass fluxes, nucleate boiling will continue. Very small sub-micron size bubbles will be there, and instead of buoyancy, the flow would be enough to pull that out, to detach them. And this is a totally unstudied area of flow boiling, how much nucleate boiling, how much convective boiling. So with using this problem, I'm trying to show its importance. Okay, this is not, but actually there is a 1970 paper by Radermacher which says he just goes all around, finally doesn't answer the question as to when does the nucleation get suppressed. So what we have done is, our research, we have not completed it. I've solved this problem assuming there is no nucleate boiling. That becomes a much easier problem to solve. Now I have Hx convective boiling formula, and I am going to compare against experiments, and then hopefully I would find an answer. That's the way we are proceeding to close this issue. Okay? When it is vigorous, when it is suppressed, how it gets suppressed. But I will show enough problems where you will see nucleate boiling is important, as you saw in this one. So with what I will do is, I would suggest, if you we have 1 or 2 minutes before if you go to these tutorials and go to tutorial 1A, the fluid properties that we entered is given in the MATLAB subroutine, which you can, when you open it with MATLAB, you can see all the fluid properties are for R1, 1, 2, 3. Surface tension as a function of is given to you for R1, 2, 3. Then Nusselt correlation of Kim and Mudawwar has been written down in terms of what is XTT, what is nucleate boiling, and what is convective boiling, and what is single phase liquid, and all these formulas are used to define H2 phase, which is here, and X2. This is just to remind that we have a tea time. So what I'm suggesting here is that if you just take the trouble, and here is the tutorial thing to plot quality versus X out, this, that, all the formulas, you can take this code and change a few numbers. Ask yourself, for a simple reason, what if this was 25 or 100 watt per centimeter? What if all the diameters being same, you reduced m dot L, m dot B, or you increased it? And you can look at the graphs and interpret it. Okay, that I highly recommend that to get better feel, and then you can even change completely the problem and go to a tube and do this kind of a problem. So I will do 2 other problems. I will do a condensing flow problem. Then I will worry about when can we see the Nusselt solution and when we cannot in an internal situation. Okay.